Okay, and then we have collisions. So we're going to start picturing objects colliding together. They have different masses, and they might start with different speeds, and we want to see what kind of speeds they would have at the end, and this relates to momentum. So there are two types of collision. There's elastic, and then there's inelastic. Okay, elastic means that things will bounce together, and they will bounce apart. So in the beginning, they might have different velocities. In the end, they also have different velocities because they have not stuck together. So elastic momentum is conserved, but also kinetic energy is also conserved. For inelastic, momentum is conserved, but kinetic energy is not. And so we're going to focus first on inelastic, and then we'll move into elastic collisions. So here's an inelastic collision example. So let's say we have one mass 1 that is 10 kilograms, and then we have a velocity of 12 meters per second. So imagine this is like an asteroid out in space, and it's coming towards this other asteroid. Now in the end, they're actually going to be clumped together. So this is going to be m1 plus m2. They're going to hit in such a way that they don't separate afterwards. And let's just say that the mass of the second guy is 20 kilograms. So that other one is at rest. The other one is going 12 meters per second. Okay. And so the momentum before should equal the momentum afterwards. So, if you think about this guy's momentum, it's going to be m times v, which would be 10 times 12. This guy's momentum, because it's not moving, would be 0. So we add those up, and then afterwards, we're going to have one clump here. And so the total mass is going to be 10 plus 20 kilograms times its velocity. Now that's the key here. We don't know what the final velocity is going to be. And so, when you have a problem like this, set up the momentum beforehand. Now in this case, those are going to add together, and then the momentum afterwards is going to be one total mass times velocity. And so what we have here is 120 equals 30 VF. Divide by 30 and we get 4. Now that makes sense because 1 is not moving. Part of the velocity is kind of swallowed up by the fact that when they collide, they're going to be a larger object, and so they're not going to be moving quite as fast. This makes sense. If you run into a car and try to push it that way, the car is only going to move a little bit. Even though you're going really quickly, it has so much mass, it's going to take a lot of momentum to get it moving. Okay, so you could have other examples like this. So for example, you could have an asteroid actually break apart. So let's say you have a 40 kilogram asteroid, and then it's going 10 meters per second, and then something happens where it breaks apart. One of the pieces, a 25 kilogram piece, goes off at 5 meters per second. So that means we have also a 15 kilogram piece going off, but we want to know how fast that is moving away. In this case, we just set it up backwards. We would have 40 total kilograms times 10. And on the right side, the momentum of this chunk would be 25 times 5, and then plus 15 times the velocity here. So, on the left side, we have a momentum of 400. We have 5 times 25, which is 125, plus 15v. This is 275 if we subtract equals 15v, so I divide by 15, and that's going to be my velocity. So the other one must be going 18 meters per second. And so it can go the other way. If things break apart, most of the velocity that it used to have is ending up with the other piece of the asteroid. So before we stop this video, we should go back here because I said that inelastic collisions do not preserve kinetic energy. So in red here, I'm going to look at the kinetic energy before, and then I'm going to look at the total kinetic energy after. Now the kinetic energy here is only going to be this first piece because it's going to be 1/2 times the mass times velocity squared. This piece, m2, does not have any kinetic energy because it's not moving. So we'll do 1/2 times this kilograms times 12 squared. And when I crunch that all, this asteroid has 720 joules afterwards. On the right side, we will be having a 30 kilogram object going 4 meters per second. Now when I work out the kinetic energy afterwards, it's actually going to be 240 joules. And so this is an important part about inelastic collisions. They don't conserve the energy. When we look at elastic, we'll see how that is an important part of figuring out your velocity.